So what is a cool star? Is that because they are low temperature or they are just cool?
Well, it's I made sure you use coldest instead of cool. I usually say coolest stars because then there's like a little, is it cool or is it cold? Their per stars are pretty cool. I mean, they're also pretty cool, but I mean, yeah.
But they are still much hotter than planets, or
Some of them, and I'm not going to talk too much today about some of our ground Earth research, but we have objects like star-like objects that are 250 Kelvin.
oh really?
So they're colder than this room. So they are really cold.
Are they dead stars?
So they're not actually technically stars because they don't use hydrogen. So they're things called brown dwarfs.
Oh, I see. Okay.
And I'm not going to really talk about. That's actually my focus of my research, but I'm not going to talk about it all today.
Oh, okay.
So maybe if I come back for another one, I'll talk about those.
Nice.
Yeah. So yeah, we study things that look a lot more like giant planets than stars.
Okay.
Yeah.
Great. Well, looking forward.
Yeah, so we'll see if I come back. We'll see how this goes first. Yeah.
So yeah, like the rule of thumb is you take 220 and subtract 30,000. That's correct.
Hello everyone. Welcome to our third GP seminar this fall quarter, and the third in-person one in a row. And so thank you for your patience, because today we finally be able to start on time, and so that we could search for habitable exoplanet with Professor Adam Burgasser. So first of all, we're very happy to have Adrian introduce our speaker today.
Great. So we are incredibly happy to welcome Adam Burgasser from Department of Physics. Now, here's the cool thing, like IGPP, right? PP, what does it mean?
Plenty of parties.
Okay, well, you know, there's a planetary in there, which we just kind of like dropped and forgot. And so there is, yeah. We are just, I mean, it's just so fun to go and actually get back to some of our roots. I mean, we have had studies on the moon and Venus, and now we get to Adam to talk to us about sort of more broadly exoplanets, coplanets. But I just want to give you a little background. So I did not know this about you. Adam got a BA in physics from UCSD in 1996. I was here, I graduated from IRPS in 1995. Now, I didn't know anything about the national championship, is that correct? The championship as a springboard diver.
When I was much younger, yes.
Okay, and not only that, so he won a bunch of NCAA awards, was nationally recognized, and just now the silver anniversary award, you must have just won that.
Yeah, that was last year. That's like, I call that the you survived for 25 years. And you get an award.
So this is an NCAA award for, it's a career award that you win 25 years later. The other thing that's just amazing is that your mentor won it. Your mentor was? Sally Ride, and she won it in tennis, apparently. Yeah. I think, okay. So all these great connections, and Sally Ride, of course, is the name of one of our newest ship. Is that truly our newest ship at Scripps? So there's all these connections. Now, afterwards, you went on, you got master's and PhD from Caltech. You were a professor at MIT, which is really cool. And then somehow we managed to get you back.
Not hard.
Okay. So 5 years at MIT, and then Adam came back to us. And there's all kinds of cool things here. I mean, we're gonna be talking about low mass stars, exoplanets. One thing I just wanted to also talk about a little bit about you talk about being a creative educator. You won the distinguished teaching award at UCSD, but you're also involved quite a bit with addressing barriers to equity and inclusion, and faculty member of the Black Studies Project and Black Academic Excellence Initiative. So it's not just about cool physics and all that, and not just about cool science. The last thing I'll say is that your lab has the coolest name on campus. Adam runs the Cool Star Lab. So, welcome, Adam.
Thank you very much. And thank you, Adrian. So it is wonderful to be here. I have been here several times, mostly sitting on thesis committees for the grad students here at Scripps. So I'm happy to be here and talk a little bit about our research. I will be talking about our search for potentially habitable worlds, potentially habitable terrestrial worlds around low mass stars, and I'll motivate why that particular very focused investigation is particularly productive, as we're seeing today. Before I go too much further, I do want to make an advertisement because I am part of the astronomy group within the physics and astronomy department. We're also centered at the Center for Astrophysics and Space Science, CAS, up on campus. And just this year, we're starting a new astronomy PhD program. And so, you know, the grad students here don't have to worry about this because you're not applying grad schools. That's great. The faculty, if you're interested in both advertising this to your students in class, but also we're really eager to make this an interdisciplinary program. So we're just getting off the floor now, so we're focusing on sort of the classic astronomy aspects. But you know, myself and Konopaki, a few others, are very interested in particularly planetary science. Because a lot of the science that we do, even though we focus on stars and really massive planets, is highly anchored in planetary processes, planetary atmospheres, formation, evolution of planets. So we would love to get faculty interested in being involved in this program. It's actually a grad division centered program, so we can take faculty from all departments and divisions. So if you want to get involved and be involved in the program, just let me know. But you can learn more about it at astronomy.ucsd.edu. This is our first application cycle, although we've actually just converted one of our physics students over to an astronomy student. So before the program even starts, we already have our first grad student. So this is starting off very quickly. All right, so today we'll be talking about exoplanets, and I always like, you know, when I'm talking to an audience that perhaps doesn't spend their, you know, entire lives breathing and eating exoplanets, to, you know, just by why do we care about planets around other stars? We got plenty of planets here in our solar system. You know, why would we care about looking at other solar systems? So I want to motivate that a little bit today, and also talk just sort of roughly about the ways that we find exoplanets, because that's going to be very central to how we design programs to find exoplanets, particularly around low-mass stars. And also what we've learned about those planets, the physical properties that we get from those planets, comes from the discovery methods. And then I'm going to focus on really the area that I focus on the most, which is looking for these exoplanets around small stars. And what I'm going to sort of show you in terms of the evidence is that both for observational bias reasons, but also for real physical reasons, it turns out that most of the terrestrial planets in the galaxy are probably orbiting small stars. And these stars are the stars that we actually know the least about, even though they make up about 70% of all the stars in the Milky Way. And so I'll introduce sort of the concepts behind that. And then I'm going to focus on a little bit on one particular system some of you may have heard of called TRAPPIST-1. This is a spectacular system. It has 7 terrestrial worlds in orbit around it, in a very compact system, 3 of which are in the star's habitable zone. And there's a question about whether this is an exception or this is just the tip of the iceberg of many planetary systems like this. And I'll give some evidence that that may be the case, that even though this was a big splash when it came out, there may be lots of systems like these. And it's just difficult at this point to find them, but there's now some programs underway to look for them. And then back some time, I'm going to motivate a little bit more about the research we do in our own lab, which is focusing on the star properties, because everything we know about the planets is anchored in the stellar properties. As I mentioned, these lowest mass stars, even though they are the most common type of star in the galaxy, to some degree, because they are so faint and so cold, they're the least understood in terms of their basic physical properties. So I'll kind of motivate why in our lab we really focus on how do we understand the stars, because that directly leads to direct constraints on the properties, including their habitability. So let me talk about exoplanets a little bit. And you know, you have to be kind of in a cave, which some of us were in the last 2 years, to not have heard of exoplanets and sort of the exciting developments that have happened in this community. It's important to keep in mind that the first exoplanet was only found as recently as 1995, when you graduated and I was graduating from UCSD. So it's a relatively new field, relatively speaking. Turns out brown dwarfs were found around the same time as well, so that's kind of a new field as well. But since that time, there have been literally thousands of these planets found around other stars, and they do encompass a huge diversity of properties. And that's actually one of the strengths of the community now. We're really past discovery science and finding all sorts of, you know, weird worlds that artists can, you know, go to town with and imagining what their colors and sizes look like. But really starting to look at this as a population. Of course, when you study populations, you start to learn things about formation, evolution, and physical processes that go on in the planet formation mechanisms. So this is a nice map of these. So what's the big deal? Well, the reason this is a great deal, finding these planets, is it opens up the possibility of comparative planetology. So we do this already in our own solar system. We look at, for example, Earth, Venus, and Mars. We try to understand why those have different evolutionary states based on their orbits, based on their physical properties, based on their atmospheric properties, magnetic properties, etc. And now with this huge diversity of worlds, we can start to expand it out much further beyond our solar system. It also tells us, it gives us an opportunity to look at both planet formation and evolution over time. And this is a classic astronomy result. If you want to understand how stars evolve over the course of billions of years, you don't study one star for billions of years. That's a really long NSF grant. All right, these are 3 years ago, right? So what you do is you look at all bunch of stars at different ages and piece together the evolutionary process for the population. And now with thousands of planets around all kinds of stars, we're able to do that in the same way. Then, of course, the other connection here is in astrobiology, looking for systems beyond Earth that might host life, and what are those conditions necessary? So to get to the comparative planetology, so again, we have our own solar system that has a pretty good diverse set of worlds, terrestrial worlds, gas giants, ice worlds like Pluto and Eris. But as we've gone out to study other exoplanets, we found all sorts of different classes of planets that just don't exist in our solar system. So here's just some of the kind of interesting ones. There's these things called super puffs, which are Jovian size worlds, but much, much lower mass. So their average densities can be, up to 20 times less than, say, Jupiter or Saturn. The mechanism which keeps these objects, which are essentially small planets with hugely extended atmospheres, what drives those formation processes has a lot to do with their evolution after they form and as they migrate in to getting closer to their stars. So there's all sorts of formation and evolution physics that go into understanding why these things exist in the first place. We have really hot worlds next to stars that are probably lava worlds in the sense that they do have liquids on their surface, but those liquids are rock and metals. We have planets that get so close to their stars that they're starting to disintegrate. We have Jovian-sized planets that act like comets. This is one of my favorite planets, HD 80606b. This is a planet that has an eccentricity of about 0.9. And so it gets in really close to its star, only a fraction of, it's like something like 0.03 AU. And the process heats up by over 1,000 degrees Kelvin and then flies back off again and cools off. And so this is not something you see in our solar system, right? If we had this in our solar system, forget about the interterrestrial worlds. But somehow the evolution of this planetary system allowed this very massive planet to essentially become a comet.
So were the super puffs rotating at all? Or why did they look so uniform?
Well, this
You
is
don't see these
the
bands.
artist rendition.
Oh, that's the
Yes.
artist rendition.
So I should be very careful. A lot of the pretty pictures are not astronomy pictures. This clearly is. This is what we imagine a really kind of foggy planet might look like. Or we have no idea. That's a good question. This is not a real picture either. That is. We have planets that are still in the process of forming, so they're extremely hot. They still have their gravitational accretion heat, so we can directly image them from their thermal energy. And then we have classes of planets that kind of go intermediate between the terrestrial planets like Earth and the Jovian planets like Jupiter. So these have various names like super Earths and mini Neptunes. Again, these are systems that don't exist in our solar system, but as I'll show in the next slide, are actually quite abundant in the galaxy. And so that's the thing, when you start to, these are all extrema, but when you start to look at the population as a whole, you can start to look at things like demographics and what are sort of the contents of our universe in terms of planets. So this is a selection bias corrected histogram of the kinds of planets that we've found. This is up to 2013, but the relative numbers haven't changed very much since then. This is based on Kepler data. I'll talk about Kepler just a little bit. This is showing kind of the relative fraction of stars with at least one planet. So the way to read this is, for example, something like 1/6 of normal stars have an Earth-sized planet, at least one Earth-sized planet orbiting around. It's important to keep in mind this is a lower limit because these are short-period planets, and it has to do with the fact that these studies are based on techniques that really only find the closest orbiting planets. So these are all numbers that are at least this many. So 1 out of 6 is actually quite an impressive number, but you move over to these kind of intermediate planet classes that go between Earth and Neptunes, which again don't exist in our solar system. They turn out to be the most common class of planets that are out there, right? The ones that we're finding most often. And again, when we correct for biases, turn out to be even more common than these massive planets, which are very easy to find. Right? Something like 1 in 5 and 1 in 5 here have either super Earth or Neptune. So again, the expansion of this population has allowed us to get new insights on what the actual exoplanets are in our galaxy at large.
Can
You know,
you help me with Neptune?
I'm sorry, say again?
I thought Neptune is also a gaseous planet.
Yeah, so it kind of like a gas ice giant, right? So
Yeah.
it's about 4 times the size of Earth. So if Earth and Neptune is kind of right at the borderline between mini Neptune and large Neptune. But these objects are probably also ice giants, although At this stage, we don't have the tools to really probe anything about the interiors of the planets. We really know, as I'll show you a little bit, is just the size and the mass. So, yeah.
So is it correct to think of large Neptune as more related to a gas giant than to Earth?
Well, like I said, this is just based on size. So Neptune and Uranus would fit into here, but so would things that are maybe between Uranus and Neptune.
But they're still gas giants, gaseous.
They're gaseous, yeah.
That's correct.
But
Okay.
what their cores are is another question. You can also look at, again, the statistics of other properties we can measure besides these basic things of mass and size. We can look at things like mass versus orbit period or radius versus orbit period. And these distributions encompass both observational and selection bias that are due to the methods that we found, but also real features. And so I highlighted a few examples here. So, there are gaps in the data like here and at long periods and at very low masses. They're almost certainly due to the fact that our observation methods can't find those systems yet, right? Something that's on a, 10,000 day orbit, we simply haven't been doing the science long enough to find those systems, right? But you can also see other gaps that emerge. So for example, this cutoff that's probably indicating the Roche lobe limit. The planets get too close to their stars, and the stars essentially get them up. You have a limit where we should be finding lots of systems based on our methods, but we find nothing. So that's telling us something about the maximum masses that are formed in planetary formation processes. You have populations that reside at, for example, very close orbits but very large masses. These are Jupiter planets that are somehow ended up close to their stars. This has been seen as evidence of migration as a common mechanism in planet formation. Again, not something that's happened in the solar system. Although there's still people who think that perhaps there's a way to make these planets, massive planets, very close to stars as well. So that's still uncertain. And then, here we see a gap that shows up kind of both these diagrams. And there's now a lot of evidence that suggests that this is actually disintegration gap. So what's happening is giant planets, as they migrate, they actually blow off their atmospheres, and you're ending up with the sort of the remnant cores. And this process is fast enough that you get this kind of gap, kind of jump between pre-disintegrated planets and post-disintegrated planets. Right? Anytime we look at these kind of distributions in astronomy, anytime you see a gap, it usually means a very fast process or a very rare process. This is probably a fast process. So these distributions hide a lot of the information of general exoplanet formation, and again, in systems that are very different from our solar system. Now, I mentioned exploring through time. So this is another place where we can get a much more holistic view of how planets form. Obviously, we can look for our our archaeological evidence of our planet formation in our solar system, but here we can actually see what's happening in real time. So for example, at the earliest stages, around a few million years, we are still seeing the circumstellar disks that form the planets. And this has been fantastic work that's been done by the ALMA Observatory in Chile. This is a sub-millimeter observatory, extremely high resolution, and of course, sampling the dust and molecular emission that comes in these cool disks. We often see these kind of gaps and occasionally spiral structure that gives some evidence that the planet is there and it's interacting with the disk and shaping it. And occasionally we actually see some emission from the planet itself. And in fact, what we think this is a disk around a forming planet. We don't see the planet itself. We see the warm disk that's around the planet that may be forming a moon in this process, right? So think about the Earth-Moon collision. There's some point where we have a disk around that, or the Jupiter system, or the moon's coalesced out of that. We might be seeing actual satellite system forming at this early stage. Yeah.
Are these optical images or they are?
These are sub-millimeter images.
Okay, so it's measuring other bands of EM waves, like shorter or.
Yeah, so this is observing mostly cold dust. So 100 Kelvin or 30 Kelvin dust, or molecular emission. So this is cold enough that you have molecules in there, and then you have these sort of molecular emission features that come out of these wavelengths. So that's mostly what's measured. Right, so this is telling us that planet formation is continuous across the first few million years, at least for this kind of stellar massive star. We can proceed even further to 30 million years. This is the HR879 system. This is a system that my colleague Quinn Konopacki here at UCSD studies in great detail. This is an example of where we can actually directly detect the planets and actually monitor their orbits over the course of many years. And in fact, one of the areas that she's studying is actually to investigate the stability of this system. These are 4 very massive planets, somewhere between 9 and 11 times the mass of Jupiter. And because they're so massive, their proximity can lead to instability. So the system has obviously been around for 30 million years, but there's some stability in the system. So looking at both the motions and then constraining what orbit parameters are possible allows us to get to study the architecture of the system. You had a question?
How are you estimating the age of these systems?
Good question. So these two systems are in young clusters. And so we can look at the other age metrics for the rest of the stars, or even the cluster dynamics. How long is that cluster at time to spread out? And that gives us an estimate of the age. And it's usually good. You know, I have little tilde marks here. It's usually good to make 10%.
That was the same
Same question. Okay, good. And then we can go even further in time. This is not that much further, but this is it's a system that's hard to see. This is a white dwarf. This is a remnant core of a star that's already evolved off the main sequence. It's depleted its hydrogen, it's injected its atmosphere, and now it's kind of a dead zombie star. And what we found at a large distance, about 20,000 astronomical units away, right? Keep in mind Earth's sun is 1. This really low mass guy, it's basically invisible in this image. That is about 30 Kelvin and has a mass of about 6 Jupiter masses, so less massive than these systems. And it's just been moving along with that white dwarf for how long it's been there. So this is an example of kind of a post-stellar, post-planetary evolution. What happens after the star dies and disrupts the planetary system? We have some evidence of planets that survive that process. So again, we can kind of see this from cradle to grave, beyond the grave, to the grave, and how planets evolve around these stars. Okay, and then again, the other question is about habitability and astrobiology. Are we alone? What are the conditions required for life here on Earth? And what are conditions required for life more broadly? Is it going to be life like Earth-like? Right? We're really expansive at this point because if you think about the entire field of biology, it's based on one experiment, life here on Earth. So what the conditions are, the energy metabolic processes, the genetic processes on other worlds, this is a really rich area, which is another talk, so I'm going to go into detail. But of course, if we want to answer this question, we need to look for planets that are, potentially habitable for life. And of course, that means we also have to define what that means. All right, so that's, I would say, some motivations for studying exoplanets. Other people have others. How do we actually find these in the first place? Well, one of the main problems is if you walk outside, is when we're studying, planets in our own solar system, it's really hard to do that during the daytime because of this damn sun. All right. And of course, what we wait to do is for the Earth to serve as a wonderful solar shield, so we can see the night sky and then detect these planets in the evening. When we're studying planets around other stars, we can't just move the Earth in the way to block its light, right? We can't do that like we do in the solar system. We need to have other techniques of essentially getting around the, blazingly brilliant light from the star that obscures reflected or in some cases emitted light from the many, many orders of magnitude fainter planets around. So there are both direct methods for doing this and indirect methods for doing this. Astronomers are extremely creative. This is a kind of a mind map of different methods that have been used or attempted to be used to find planets. As I said, sometimes they're direct, where you literally block out, so in direct imaging, you literally block out the light from the star and you can see the planets around them. But most of these are indirect, looking for perturbations from the planet on the star. For example, it's Doppler shift. We'll talk a little bit about that. Or the planet passing in front of the star, blocking its light for a very short amount of time. We even use things like microlensing, which is how planets will actually, through general relativity, slightly brighten the light from the star, just like a lens. And we can see that brightening profile and infer the mass of the planet from there, because it's a gravitational effect. So there's lots of different ways that we use to find these planets, and all of them probe different properties of the planets and the systems themselves. So the first one, which is originally sort of the most popular one in the beginning and found some of the first exoplanets, is something called radial velocity method. And this is something, I'll show this video in my physics 1A class when we talk about Newton's third law, because this is really what's happening, right? We talk about planets orbiting stars, but of course, the stars are also in those orbits. They're both orbiting a common center of mass. And so what we can do is watch the star. We don't see this planet at all, but we watch the star and we see how its spectrum is shifted back and forth in velocity space by very small amounts. And by seeing this as a periodic motion, we can infer both the orbital radius and the mass of the planet, because again, that's a gravitational interaction. This was the first method that was really deployed to find, I'd say, the bulk of the planets up until the early 2000s. Of course, one of the first ones was 51 Pb. If you think about how this method works, again, it's the planet pulling on the star. So this is going to favor massive planets on very short orbits, right? And that's exactly what happened when 51 Peg B was found. It was a complete shock because most people studying the solar system as a template would say you would never find a Jupiter-mass planet close enough to the star to actually do this. And in fact, this is what those two discoverers, Mayor and Taylor, did back in 1995. They monitored a star, noticed its radial velocity perturbation. This is actually what the radial curve looks like. And we're able to measure this back and forth motion and measure both its amplitude, which of course is proportional to the mass. How fast the star is kind of reflected back is a function of the mass of the star or the planet. And then of course, the time between the successive peaks gives you the period, the orbital period. They of course won the Nobel Prize for this back in 2019. There's many other things that can be measured from these radial velocity curves, by the way. The shapes of these curves can be distorted. That gives rise to eccentricity. You can see multiple planets, multiple radial velocity sine curves that get imprinted on each other. So there's a lot of information that comes from this. But again, this was the first method to be done because it was able to exploit the fact that we can make extremely sensitive velocity measurements. This is back in 1995, and they were able to measure the velocity of the stars down to 50 meters per second. In fact, the uncertainties here are closer to about 5 meters per second. Today, we can do even better. So this is a recent result from a few years ago that found a couple of planets around our nearest star, Proxima Centauri. And look at the masses here. These are 1.6 and 7 Earth masses. Again, at close separations because you need to actually see the whole waveform happen. But notice the scale here. This is measured in kilometers per hour. So these are Europeans, which is still kind of mixed units. But if you're driving in traffic in kilometers per hour, you know how slow that is, right? So these are incredibly sensitive measurements. And we've gotten down to measuring velocities on the order of centimeters per second in making these detections. Centimeters per second, right? Being able to do this for stars that are way outside our solar system really exploits the ability that we've been able to develop in the sensitivity of this measurement, again, just by looking at spectral lines moving back and forth. By the way, for this one, you'll notice that you have kind of a sine curve that's highlighted for this, but also a decreasing trend. And that's why we think there are 2 planets here. We know there are 2 planets now, is that you're seeing these, again, these superpositions of 2 periodic signals, and you can disentangle that to figure out the masses and radii of both planets in the system. And there may be more. We're still looking. All right, the other method that's very common is the transit method. This is using the fact that if a planet happens to pass directly in front of the star and you're monitoring its brightness, it will very briefly block the light of the star, and you'll detect a small dip in the light curve as the planet passes around. And of course, if you keep staring at it, you'll see that dip appear again and again on the orbital period of the system. Now, again, based on this, this really favors very closely separated planets again, right? You need to have these happen a few times before you believe it. And it favors physically large planets, not necessarily massive planets, but physically large planets. This really didn't take off until about 2000 at the start of this millennium. You can see this is the first measurement of transit. This is actually for a system that had already been discovered by the radial velocity method. So they knew the planet was there, and they were just trying to see if they could catch one of these transits. Keep in mind that this requires an incredibly accurate geometry, or very precise geometry, right? This planet has to line up and cover the stellar disk. And on sort of just a random basis, it's about 1% of star systems. If they all had planets, this would be the case for, say, an Earth orbiting the sun. So this is a very rare opportunity. But they're able to make this detection. You can see that it's extremely small. It's about a 1 to 2% dip in light. There's, by the way, lots of other things that are making the star's light bounce up and down. So you also have to correct all those things. This is back in 1999. This is a more recent measurement of the same system. You can see how improved our precision has gotten in this technique as well. Same dip here is completely obvious. And in fact, it's so clear, you can even see the planet passing behind the star, its reflected light being obscured. And also the phase of the planet as it's going around as well. Right? That sort of visible curve is coming around and then getting blocked on the backside, and then we're seeing the dark side as it comes and blocks the star on this side. So we're seeing actually now quite a lot of detail from these transits because our photometry is truly exquisite, parts per thousand. So this has been an extremely popular method. It's found, as I mentioned, something like 4,000 of the planets that we know today, 3,000 or 4,000 of the planets we know today. And again, based on the measurement, we can get a lot of information about the planetary system. The depth of this dip is proportional to the size of the planet. It's actually proportional to the ratio of the planet area to the star projected area. So you need to know the star's area to do this. Duration is obviously related to the orbit. The shape of this curve is related to where the planet actually passes in front of the star. One thing that's not as obvious here is that you can see this picture is actually indicating what we know as limb darkening. The fact that stars are actually a little bit darker on the edges as opposed to straight on. This is an opacity effect in the atmosphere. And so depending on where it passes through, you'll get sort of different curvatures on the curve as it ingresses and egresses. And then the timing, as I'll talk about later, is also very important because we'll see this is actually one way of measuring the masses of planets if there's multiple planets in the system. And there's all kinds of other things you can do in this case, which I'll refer to occasionally in this talk. There are things like transmission spectroscopy, actually seeing the light pass through the atmosphere of the star when it's passing in front. You can measure the atmosphere that way. I showed you can measure the secondary eclipse, the phase curve. There's other things like spin orbit alignment, looking at how the radial velocity of the planet changes or the profile changes as the planet blocks the approaching and receding side of the star. Multiple planets, moons, there's all kinds of things that we can do with this method. Right? But again, it requires you to get really lucky. Right? You have to just happen to have the right geometry to see this. And so just pointing at a random star really doesn't work for this technique. You've got to point at lots and lots of stars.
So for those black dots there, those are an ensemble average of over some number of snapshots or whatnot, or is that actually one measurement?
These individual points are individual measurements because the time scale for this is typically something like an hour or two. So you're often integrating, and it depends on the experiment, you're often integrating kind of 5 minutes on each image, and you're just taking that measurement. Now, there's a lot of calibration, of course, that goes into making this. So
Right, okay.
there's processing that goes into
So
it.
there's like a 5-minute integration time.
Yeah. But again, this highlights just how precise these measurements have gotten over time, in part because we're really relying on space telescopes to make these measurements more than ever. So again, the way that this has really exploded thanks to spacecraft telescopes that are dedicated to these things. One of the most important of these missions was the Kepler mission, which was launched back in 2011, I think. This pointed at just one part of the sky, but that one part of the sky had about 100,000 stars in it. And so you're kind of playing the odds, right? If 1% of stars are going to have the right geometry, and you point to 100,000 stars, you have a good chance of finding quite a few planets. So this is the field of view that it looked at. It's just above the galactic plane. So it also was able to study different populations in those field of views based on what part of the galaxy we're looking at. The K2 mission happened after all but 2 of the gyroscopes in Kepler failed. And they figured that they could keep the pointing by kind of using the 2 gyroscopes and kind of the interaction of the Earth, the telescope, and the sun to keep the telescope in line for like a month or 2 at different positions along the ecliptic plane. So this mission kept going after it was formally broken and actually got quite a bit more data that people are still pouring through there. But this is a very small part of the sky, right? 1/4% of the sky, about the size of 2 full moons across. A more recent survey that just launched back in 2018 and is currently undergoing observations called TESS, or Transiting Exoplanet Survey Satellite, is doing exactly the same process, staring at areas of sky with very high precision cameras. But in this case, they are mapping across the entire sky, right? And so they're getting a much broader view of planets around in all directions. However, Kepler stared at this sky for 3 years, and TESS is staring at these skies anywhere between a month and a year, depending on where the location is. So you're trading off surface area for temporal time, right? And again, time means you get to see longer orbital periods, more rare transits, stuff like that. But nevertheless, TESS has so far found something like 4,500 potential exoplanet transits, and people are following them up today, including Earth. So there's a lot of activity in this, and of course, once you find a lot of these planets, you start to find lots of interesting planets. And I think one of the goals, of course, for Kepler was to find a potentially habitable Earth-sized world around the sun. That's or sun-like star. That's why the mission had a 3-year lifetime, right? Sun Earth-like planet around sun-like star is a 1-year orbit, so you need to get at least 3 of those transits to prove that. It never achieved that. However, it ended up finding lots of potential habitable worlds, not of the kind that was originally intended. So the first of these terrestrial potential habitable worlds was found as recently as 2014. We should have a lot of pride here at UCSD because it was found by UCSD alum. This is Lisa Quintana. She actually went to UCSD with me as an undergraduate student in physics. Worked with Sally Ride as well. And she worked with the Kepler team to uncover this source, Kepler 186F. Now again, artist rendition, not what we really see, right? All we see is just these light curves, right? That's what we measure. This is what we imagine. But this is a planet that is, again, relatively close to its host star, but that host star is a low mass star, about half the mass of the sun. And as I'll kind of emphasize a little bit later on, that is actually a key point because, as we'll see, these low mass stars are extremely common, and their habitable zones are really close to the star themselves, which means the probability of transit is much higher. So at some level, the odds are particularly stacked finding these kind of planets if they exist. And what we found is that they do exist. So again, the equilibrium temperature of this planet, all else being equal, we're not including atmospheric effects here, is somewhere on the order of 260 Kelvin or something like that. So it's a good candidate for having liquid water on the surface. We don't know that, of course, but this is the first case of this. So 2014. Since that time, and this is a little bit, it's about a year out of date now. This is a compilation retained by the University of Puerto Rico lab at Arecibo. We have something like 24 now, potentially habitable worlds, and they have kind of an index to measure this. We'll talk a little more about potential habitability in just a second. But the important thing is that all of these worlds, and again, these are just imagined, figures. We don't really know what they look like. We don't know if they have anything on their surface or atmospheres or whatever. 23 out of 24 of these are orbiting stars that are much lower mass than the sun, half solar mass or less. So why is that? Why, when we're seeking an Earth-like planet on a sun-like star, we're instead finding these habitable planets around, or potentially habitable planets around these little inconvenient stars? So that's kind of the question for the next part. Yeah.
So what's the number in the bracket for each planet?
Yeah, so this is called the Earth Similarity Index. You'll notice that Earth is exactly 1.0. They use kind of different metrics of the equilibrium temperature, the size of the planet, the composition of the planet that's known, properties of the star itself, to come up with kind of a number that tells us how like it is. It's a totally useless statistic, so don't read it too much because we don't know anything about the planets themselves, and that's actually an important point to make about habitability, which we'll talk about in just a moment. Any other questions at this point? Yeah.
What's the farthest? Is it just in our own galaxy, or is it?
Yeah, we're constrained to our galaxy mostly because of sensitivity limits, but within that, I think the furthest planet is several thousand parsecs or several thousand light years away from the Earth. Particularly that radial velocity method, as long as you can detect the star, it doesn't matter how far away the star is, because all you're looking for is the shift of the lines. So that's kind of independent of distance up to the point where you can't see it anymore. So we find these things literally all over the galaxy to the limits of our sensitivity. So let me talk about potential why we're finding some of these potential habitable exoplanets on small stars. And the answer is it's kind of a mix. It's kind of like the news today. It's both bias and truth, right? So first of all, I want to make sure I'm clarifying when I say potentially habitable worlds. This has a very specific definition for astronomers. And it's the region around the star where, based on the star's insolation and of course the distance of the planet to the star, you have a possibility of having liquid water on the planet. Now, there's a huge number of caveats to that, right? All we're determining here is effectively a neutral albedo equilibrium temperature for the planet. We have no idea about the actual atmospheric conditions of the planet, if it has an atmosphere, the surface conditions. There's a lot of other things that can change this over time. For example, the stars themselves evolve over time. They get brighter as they go through their hydrogen store. So this habitable zone moves outward. We should worry about this a little bit because we're kind of on the inner edge there. The orbits themselves can evolve over time. We see that with migrating planets, and of course the planet properties. The case I always give is that Earth is, obviously a beautifully habitable planet. We're in the right spot for the sun, but the moon is too. Not such a habitable planet, right? So the planet properties matter a lot. In some cases, they're more important than necessarily the distance to the star. But this is the limit of our ignorance, right? We only can measure this point, the orbit distance, and properties of the star. It's really going to be in the next generation of telescopes where we can start probing the planets themselves. Now, as I mentioned, when we get to low mass stars, these habitable zones move in much more closely because those low mass stars are both cooler and lower luminosity. So this is a plot showing the host star temperature versus the distance for planets. These are all kind of the planets that are known today in this diagram. And this red line kind of maps the sort of, you can roughly think of this as the freezing to boiling point at the temperature, at the surface of the planets. And you can see that in the range that we're mostly interested here, which is very low temperature stars, these distances are on order of a few hundredths of an astronomical unit. Now, for comparison, Mercury is about 0.3 astronomical units from the sun. So we're talking about planets that are 10 times closer to their stars. But of course, the stars are much, much cooler. So that is still a habitable region around the stars. Now, being so close, this actually helps with many of these detection methods, particularly radial velocity in transit. So when an Earth passes in front of a sun-like star, Earth is about of order 100 times smaller in radius than the sun, so the projected area is about 0.01%. Right? When the same planet passes in front of a low mass star, oh, I need this animation. You increase that signal by a factor of 100. Right? So you're really improving your ability to detect these things by going to smaller stars, because what matters is the ratio of the planet area to the planets of the star area. And as I mentioned earlier, low mass stars are extremely common in the Milky Way. So this is a fun graphic showing as a function of different spectral types, and I'm not going to talk too much about what these spectral types are because it's definitely astronomy jargon, but these are the high mass stars and these are the low mass stars. And this is the sample of stars that we know about within 25 light years, so kind of our local solar neighborhood. And you can see that as we go from high mass stars to stars like the sun, so the sun is one of the 8 in here, to lower mass stars, you get this huge jump in number. Right? So something like 70 or 75% of the stars in our galaxy are stars that are in this M dwarf class, and that's again about half to a tenth of the solar mass. Interestingly, we can see none of these with our naked eye. If you go out in a beautiful dark spot, you will never see an M dwarf there. It's just simply too faint. And that's an important limitation for studying these things. You need telescopes and big telescopes to do the kind of studies for these things. But they are extremely common. They're also extremely long-lived. The lifetime of a star depends on how fast it's burning through its hydrogen store. And because M dwarfs are very low luminosity, they're doing this fusion at very low rates. So, the typical M dwarf lives for about 100 billion years. Keep in mind, the galaxy is only about 14 billion years old. So every one of these objects formed in the history of the Milky Way is still around and is very happily and stably fusing hydrogen. Will do so for a long, long time. These are very stable systems. And so these are part of the sort of selection effects. The other thing that we're finding is that indeed these planets, these kind of stars seem to make more terrestrial planets. So let me talk through this diagram a little bit. This is again showing stars of different types, going from hot stars, massive stars, sun-like stars, down to our low mass stars. And what's shown here are different estimates of the number of planets per star with some caveats, right? So these are short period, less than 10 days. Radius range between half an Earth mass and half an Earth radius and 2.5 Earth radius. This is just based on the selection criteria. And what you can see is that the rate goes up as you go to lower mass stars to the point where it gets over a planet per star. Every star on average has one of these low mass planets. Again, 0.5 to 2 Earth radii. And even when we zoom in on this kind of range here, you can see that even as we go through there in more detail, it seems to also climb even further. Again, this has all been corrected for selection biases and stuff like that. And so it gives some evidence that in fact, terrestrial planet formation is much more common. I mean, that's what we're looking at around low mass stars than stars like the sun. Now, at some level, that shouldn't be surprising because the disks that form these low mass stars are proportionally smaller in size and mass. So the amount of material available for planet formation is depleted. And so you would expect smaller planets. But it appears that even the process of formation around these stars really favors terrestrial planet formation over giant planets. It is more efficient in terrestrial planet formation than stars like the sun. So lots of stars, and they are more common terrestrial planets. You easily equate that these are going to be the overabundantly well-named largest sample of terrestrial planets in our Milky Way. And indeed, one of my colleagues up at UC Irvine, Alamo Shields, made this kind of statement that if we really want to understand search for habitable worlds, we really need to probe the M dwarf stellar environment. What kind of planets are around these stars, and particularly what we know about the properties of these stars. That's really the motivation to focus on these kind of planets. So this kind of encapsulates this this trend. So when you look at the probability of a transit, so this is based on the transit method, the probability of transits, the depth of the transits, the number of orbits you see every year, all of those statistics improve as you go to very low mass stars. So the argument is that small stars are beautiful for this work, and that's what we should focus on. All right, so I'm going to focus on one star, and I do want to keep mindful of time so I can talk a little bit about some work we're doing there. So I'll go through this a little bit quickly. So one of the first examples of these very low mass star planetary systems we found, as I mentioned, is TRAPPIST-1. This was detected by the TRAPPIST telescope network. TRAPPIST stands for Transiting Planets and Planetesimals Small Telescope. We think it's a very tortured acronym. It spells out the name of a very popular beer in Belgium. And that was actually the point. This is the Belgian project, and they like to name their projects after food or something. So this is a half-meter telescope, relatively small telescope, located in Chile. There's a complementary site in Morocco, same kind of telescope in the northern hemisphere, so we have coverage both north and south hemispheres. And starting in 2014, we did a sort of initial survey just to kind of test out the system and see if we can actually make the measurements at the precision we need to find planets around these low-mass stars. So this is an image of the field around TRAPPIST-1, one of the objects that was in that first sample. We can't see it. It's actually here. You can't see that. It's this tiny little faint red dot right in the middle. Right? This star, as I mentioned, these are very dim, low-mass stars, very hard to see. The star itself wasn't known until the year 1999. Right? So these are relatively new discoveries, even though they're pretty close to our solar system. And in early data, we were able to start to detect these multiple transits around this star. So this is actually based on several different telescopes, including the TRAPPIST telescopes. What we found was that there seemed to be 2 planets in the system that had very short periods, 1.5 and 2.4 days, at the entire orbital period, very close. And then kind of a rogue transit that we couldn't match up with either of these periods. And so when this first discovery came out in 2016, we knew that there were at least 2 planets in here and something was out here. And this something was interesting because it was somewhere in the range of where the habitable zone of this planet, the star was, but we couldn't actually determine it from one transit, right? You need more than one transit to figure out the orbit. And again, very compact, only about 0.03 AU in the total diameter of the C orbit here. So 0.015 is the radius. So we kept monitoring it, and in 2015, right around Christmas time, or just a few weeks before Christmas, we got this transit from the system from the TRAPPIST telescope. And often when you see this kind of data, you think, oh, something's really wrong, right? Somehow maybe there's like a satellite that went through our image, or CCD freaked out. But one of the graduate students in our team said, well, I think I could model this, because we knew, for example, that the transit depths were on the order of 1% or 0.5% or so. And so what he figured out is that you could actually model this curve, and that's what the red line here is, by assuming that not one planet, not 2 planets, but 3 planets that actually pass in front of the star at the same time. Now, we had previously seen in other systems double transits, and that's how we knew the existence of some multiplanet systems. It's the first time we've ever seen 3 in a row. And to see 3 in a row is pretty rare unless you have a lot of planets around the star. And so we use this to motivate a campaign using multiple space telescopes, ground-based telescopes, to literally stare at the star over the course of months. This is a time series of the data from the Spitzer Space Telescope. So this is the actual data. This is a model of the planets going around the star. And so every time you see a thing go in front of the star, that's a dip in light curve. And of course, they are all these different periodic signals that come very regularly across. So we're able to disentangle this information to figure out the orbital periods of all these planets. And when you go through this process, you find that they're not just 2 planets or 3 planets, but there's actually 7 planets in the system. So this is what we measured in 2017, right? A vast improvement over what we knew in 2016. And in particular, these 3 planets here in the middle were at the right distance from the star to be in the habitable zone, potential habitable zone from the star. So 3 potential planets, that's really amazing. But just the fact that we found 7 terrestrial planets in one world is also a top kind of record. Okay, so I'm going to jump ahead a little bit. So one thing you'll notice about that is that they're very compact orbits. In fact, they're in a resonant system, very much like the moon system around Jupiter. The orbits are in integer ratios, nearly integer ratios. They're slightly off as you get further out. That suggests that there has been some migration and evolution in this planetary system. They don't usually form resonant systems, but they will sort of evolve into these resonant systems. And so again, that tells us something about how the system formed. But the proximity of the planets to each other also turns out to be really important in understanding their physical properties. you zoom in on each of these transits, what you find is they don't exactly line up at one orbit period. They drift a little bit. So sometimes they come a little early, sometimes they come a little late, sometimes they're smack on. That transit timing variation is due to the mass interactions between the planets themselves. They're pulling each other either a little bit faster or a little bit slower through the orbits. Because that's a mass interaction, that gives us a way of measuring the masses of the planets, which we can't do from a transit method. Now you need hundreds of these to do this, because it's a statistical process. You're looking at an 8-body system and trying to figure out the masses as they interact with each other. And this is kind of what this looks like. So all the orange lines here are the variation between the periods, expected periods, and what they actually determined, and the predictions from our best model for the mass interaction between these. So you see these very wiggly lines, and you can see we very clearly match these transit timing variations quite well. And as a result, we get not only the size of the planet, but we also get their masses. And then we can place that on, say, a mass radius diagram. And what we find is these planets lie exactly on the same compositional lines that you would expect for our own terrestrial planets. So there's no, we're very sure that these are terrestrial planets. They match up in terms of density. They line up very well with the compositions we expect for our own terrestrial planets. And in fact, you can extend this even further out to masses up to 10 times the Earth mass. And you can see that many of these planets, besides TRAPPIST-1, but also others, are falling along this nice curve. So to me, it's interesting we haven't found large deviance, but this does indicate that the formation of our terrestrial planets in the solar system is probably a very similar process to the formation of these planets as well. All right. So I'm going to skip ahead a little bit, and I'll say just at the side that, you know, there's more than TRAPPIST-1 out there. There's another star called Teegarden star that has a couple of these small planets, and there's several efforts underway now to look for more of them, including some efforts that I'm helping out with for the sort of follow-up for TRAPPIST. And our postdoc, Chris Tyson, is also working with a group at Boston to look for even lower mass co-stars. But I want to motivate a little bit about why we're studying the stars themselves. Keep in mind that all the properties I talked about, mass, radius, orbit, the subdegrees, or the composition, how these stars are made, the planets are made, come from looking at these fundamental properties of stars themselves: their masses, age, radius, temperature, luminosity, composition, magnetic activity, and multiplicity. Some of these we can observe directly. Some of them we have to infer from combining the observations with models. And it turns out it's hard to do this for low mass stars. So if we look at age dating, for example, you know, there are books on how to do this. This is a very standard process. What we essentially do is we look at secondary characteristics that evolve over time. We calibrate them to stars that have ages. So that might include the decline in rotation and magnetic activity that comes from stellar winds that take away the torque on the stars, or slow changes in the atmospheric light element abundances as they get kind of pulled into the core and destroyed through fusion, and stellar evolution. It turns out these trends and techniques do not map themselves out for this low mass regime for various reasons. So we have to develop new ways of studying this. So for example, for TRAPPIST-1, we couldn't use any of the standard age techniques, so we used statistical methods. We looked at the local population of stars, we looked at their kinematics and their abundances, their chemical abundances, and we're able to essentially make a statistical argument about what similarity TRAPPIST has in terms of its neighbors. And from that, we were able to constrain its age pretty well to something like 7.5 billion years, which is interesting. It's 50% longer than the sun. So obviously there's a range of uncertainty here, but that means this, whatever the system is, it's been around for a long time, right? So those planets probably stabilized in some stable configuration. And, you know, if you're looking for life, that means it's been around there for a long time. I have a student, Jessica Berkey, who finished a couple of years ago, who's looking at high resolution of spectra and using machine modeling methods to essentially take a few calibration stars and then map all of these features into a way of essentially determining things like metallicity and spectrotype. So for example, this is a diagram showing absolute magnitude versus color for stars that she has actually computed the metallicities for. And you can see there's actually a trend between how bright the star is and its metal abundance. So these are metal rich, these are metal poor. By the way, metals for astronomers is everything except hydrogen helium, so it's everything. And so this provides now a map for how we can take very basic properties like the brightness of the star and infer the actual chemical abundance. Right. So very important statistical techniques. One of the things that we're particularly interested in is for habitability is flaring, right? Magnetic activity. This is a light curve for TRAPPIST-1 taken with the Kepler Space Telescope, and you can see there's these little, we talked about the dips, but there's also occasionally little pop-ups. These are magnetic flares, just like the sun has. Although this magnetic flare actually made the star twice as bright as it was in the preceding time. When you measure the energy of this, it turns out to be appropriate for what's known as the Carrington event, which is a 19th century flare that the Earth experienced from the sun, that caused like telegraphs to start, operating on their own and all sorts of disruption. Keep in mind, 19th century, there wasn't much of an electronic grid. So this would be super expensive today, very disruptive. And it turns out these stars do these kind of Carrington flare events almost all the time. It's a study from my colleague, Sarah Schmidt, looking at the total energy from flares of different stellar types. The Carrington event is about 10 to the 32 ergs. That's actually below the lower axis on this plot. So many of these stars are emitting flares that are 100, 1,000, 10,000 times stronger. Keep in mind that the planets are also much closer to the stars if they're inhabitable. So these stars are experiencing extreme magnetic environments. There's been studies to show that those magnetic fields are so strong they'll actually connect with the planetary fields and directly deposit charged particles on the surface. We see this again in the Jovian system, but not in normal planets. That activity is enough to dissociate water, if there is water on the system, actually remove that water through dissociation and photoevaporation. So there's estimates that TRAPPIST planets might have something on the order of tens of Earth equivalent oceans that have evaporated over the course of its lifetime. So if there was the potential for water, perhaps that water is no longer there. That has another effect, that water, as it dissociates, the hydrogen leaves, but the oxygen stays. So you can end up with an oxygen-rich atmosphere, right? So this is showing some estimates where the oxygen abundances, for example, O2 and O, can be of the same order as the mixing ratios of things like hydrogen and carbon monoxide. So you can be fooled to thinking that I see this oxygen-rich atmosphere. It's not biotic. It's this process that's essentially desiccated the atmosphere. So there's all sorts of caveats that we have to use and study these things because they are very different kinds of stars than we study. So our group focuses on studying these properties and developing new systems. We use resources of liquid tech to essentially measure spectra for these stars and characterize them. Something like 50% of the stars near the sun have never been observed in this way. This is just a big oversight because no one was really interested in them until they had a lot of planets. One of my undergraduate students from last year actually discovered a new star in this process that was able to characterize that using the CAST spectrograph from the Lick Observatory. And then we're also expanding out to other populations. So my grad students here, Dino, Christian, and Roman, are studying different aspects of the local population to start to build these statistical techniques. So Dino, for example, is looking at kinematics, the motions of stars in three-dimensional space, to start to constrain the ages of these systems, right? Both as a population and individual. Christian is studying populations at large distances. So we mostly focus on stars that are within maybe a few tens of parsecs from the sun. He's been building samples that are thousands of parsecs away from the sun and seeing how those properties vary as functions of galactic distance. And then another graduate student, Roman, is looking at populations in globular clusters, which are these really old clusters that have different metal abundances. And again, as a way to kind of see how we can infer compositions for low mass stars when we look at the extra. Okay, so thank you for your patience. I would put the summary point up here. I think the key point is that when we think about exoplanet science, I think for many years it was just, wow, look at all these great planets. They're really cool and they have like different properties and great artwork, right? But really moving to the point where demographics and statistical studies are telling us a lot more about how planets form in the galaxy at large, not just in our solar system, which turns out to may not be the sort of template for most planetary systems. And so we're looking at this both over time and in different types of environments. But it's really that when we talk about habitable planets, it's really the low mass stars that we want to focus on. Because it seems that terrestrial worlds, and particularly terrestrial worlds in the habitable zones, are more common in these stars than others. And there's a lot more of them. And unfortunately, we just don't know much about the stars themselves. So we're working on figuring out ways of characterizing those stars, both statistically, using, for example, machine learning methods, but also the resources that we have at UCSD. These are great student projects. So I showed some examples of students, but we have teams of undergraduates that are studying these data and learning all about things about stars, and also telling us about some of the stars that are potential planet hosts. All right, and I'll take any questions. I know we're a little bit late on time, but I'll take any questions if you have them. Thank you very much.
Yeah, I wonder if you could talk a little bit more about what we know about the magnetic environment, because you showed these exciting magnetic properties of the stars. But how does that translate into what you know about the planets? And you also mentioned that there was this decoupling of the atmospheric atmosphere and magnetic field. I wonder how you know that.
Yeah, good question. So let me go bring up the thing, this plot. So, so first I mentioned, so we do actually know quite a lot about magnetic fields, although they're not, we study magnetic fields around other stars, for example, stars like the sun. There's a lot of tools we can use. We can look at Zeeman splitting lines and sort of Doppler shifts of Doppler splitting of lines in the stellar spectrum. We can look at sunspots. We can look at X-ray emission, UV emission. When we get down to these low cool stars, so in this plot, this is going from kind of a half a solar mass down to maybe less than a tenth of solar mass. We see some unusual things happen. First of all, the stars become overall much more active. Right? Something like 100% of these very low mass stars are either steadily emitting high energy radiation or undergoing these large bursts. So in that sense, it means that the systems that are orbiting this are constantly bombarded by magnetic flares. Keep in mind that for this light curve is, I didn't measure the units here, but this is measured in days. So in the course of just 120 days, this thing went through a cataclysmic flow. It likely does this a lot. And it turns out that TRAPPIST-1 is actually a low activity star for this type of thing. So we know that these stars are very active. We have estimates for the magnetic fields. They're few kilogauss, which is the average across the entire surface. For comparison, the sun's about 50 gauss on average and a kilogauss in the sunspots. So these are far more active than sun-like stars. These stars are the sun. Now, what I don't show here is that after you get below this temperature, there seems to be a sudden change in the magnetic properties, and that's probably because these activities are really driven by magnetic reconnection events because you've coupled the magnetic fields with the plasma atmosphere. That's what drives sunspots and flares from the sun. At some point, the atmosphere becomes so cold that it becomes neutral, and so these magnetic field lines are no longer being pulled around by the dynamic mixing of the atmosphere, and we lose all of that activity. It doesn't mean we lose the magnetic fields. And so we see, for example, evidence from radial emission that these magnetic fields are still very strong when we get to cooler temperatures. And some argue that the magnetic emission is not from the star itself, but it may be interactions between the star and the magnetic fields of the planets. And that's a speculation. We don't actually have the operation to confirm that. Other thing that's important to think about is that when we talk about habitable planets, they're so close into the star that they're synchronously rotating. So say a 5-day orbit planet is also rotating in 5 days. So its rotation rate is so low that it probably doesn't have a significant magnetic field of its own. So it's experiencing kind of the full brunt of the magnetic environment of the star. So people worry a lot about this for habitability. And people argue on both sides that this is terrible for habitability and it may be crucial for driving mutation rates, stuff like that for habitability. There's no consensus on this. But it is an important factor for understanding the environments around this planet. Yeah.
So you have introduced 2 methods of detecting those exoplanets, but in your following talks, you have been mostly focusing on one, the transit method. So what happened to the other one?
Nothing. It's still there. Part of the reason the transit method is so useful is that it can be done with relatively small telescopes. And so as long as I can park my telescope to point at one particular star for as long as I want, or a region of stars, you can usually get enough of the signal to detect the transit. The radial velocity method requires very high resolution spectroscopy. So that needs big telescopes because you're taking the light and you're spreading it out in a spectrum very finely, right? These spectrographs are 100,000, 200,000 resolution. So the data from RVs usually come from the largest telescopes. And to study a whole population of stars with the largest telescopes is hard to do because everyone else wants to use the large telescopes too. Whereas the TRAPPIST telescopes are only half-meter telescopes. Those are tiny in comparison. So a lot of the transit programs are able to capitalize on the availability of small telescopes that can just be dedicated to that survey, as opposed to the radial velocity method where you really have to compete for the time. So that's part of the reason that, at least on the ground, transit is long. And then for space, transit satellites are much easier to design than the equivalent radial velocity ones. Again, because it's just a camera. TESS is literally just a set of Nikon cameras pointing out into space. Much better CCDs, but that's the kind of idea. So they're cheaper missions, they're easier to design, they're lower hit rates, right? Again, because you have to have this geometric luck, and you have to time it as well, right? Ground-based is kind of hard because you can't observe during the daytime. But nevertheless, they're much cheaper missions. So that's why you're seeing a lot of transit programs, and that's why I'm focusing on that. Other side of this is that transit gives you more information. So in addition to, you get the size and sort of orbit properties, when the light passes through the atmosphere, you can measure the atmosphere. When you can see the backside, you get something about the actual surface properties. There's a lot more information that comes from transits than just radial velocity.
So is there any real advantage of radial velocity method over the other one?
Well, the best thing is to do both, right? So if you can measure transit and radial velocity at the same time, one of the constraints for radial velocity is you only get a projected mass, because if you imagine if your planet's going around like this, it's going to pull the star, at sort of its maximum value this way. But if it's tilted this way, you're only going to see the component of radial motion of the star that has to be aligned. So you actually have a geometric, sort of uncertainty in the mass. If you know it transits, you know the configurations like this, and you can exactly measure the mass. So the best systems combine radial velocity and transit. But again, particularly these low mass stars, that's limited by our ability to actually measure those radial velocities because they're so bright. Yeah. I think there was a question online.
Yeah. So Dan, would you like to unmute yourself and ask a question?
Yeah, thanks, Adam. This was an amazing talk. I absolutely loved it. It was very informative. I was wondering about the influence of greenhouse gases on the habitable zone. So when you calculate the habitable zone, do you consider that there might be a runaway greenhouse gas effect on the planet? Like say Venus was orbiting further out than Mars. Would that still be part of the, the habitable zone for our star? And do people consider that, or is the habitable zone potentially much larger than sort of astronomers cite when they're sort of doing their studies, because greenhouse gases aren't included?
So actually, it's probably the opposite, that it's smaller than we assume, right? So I'm trying to get back to the habitable zone slide.
Dang, that's too bad.
There. Sorry about this. So the answer is yes, people do worry about this quite a bit. And so you probably can't see because the greens kind of come out a little bit differently, but there's actually two green bands in this image. One is a conservative habitable zone, which accounts for the fact that planets that are close in are probably being affected by greenhouse effects. So we call that kind of the Venus limit. And then as you go further away, these actually line up pretty well, but you can also consider other effects of freeze out of the atmosphere, for example. The other thing that's important is that this is a snapshot in time. So as I mentioned, stars evolve over time. So another thing that's often used is called the continuously habitable zone. And that accounts for the fact that this zone has to move out as the star evolves. And in fact, if you use that criteria, the Earth is not in the continuous habitable zone, because in about 1 billion years, the sun will be so bright that the Earth is probably going to undergo a greenhouse heating no matter what we do. Right? So, enjoy your life now. But in any case, yeah, people do worry about all these properties. And, to some degree, it's important to keep in mind that this is a very rough ansatz, because it doesn't link at all to the planet properties, right? We can link to sort of statistically what might happen at the edges. But until we know what the planet's properties are actually are, and of course that relates to size, magnetic field generation, the atmospheric properties, we can't say whether a planet is potentially habitable or not, or whether it has water on the surface or not, until we actually get those planet properties. So this is a rough idea, and people do play around the edges, but it should only be a guiding principle, or at least a way of finding kind of the most likely planets. But there's no guarantee that the 24 I showed earlier, any of them have liquid water on their surfaces. That's one of the things that we're hoping James Webb will help us figure out, is it will have the sensitivity to start measuring the atmospheres of some of these planets that are transiting the stars using this sort of transmission spectroscopy method, which I didn't get a chance to talk about a little bit, but that's something we're looking forward to.
Thanks, Adam. Appreciate it.
Yeah.
I was wondering if you could go into a little more detail about the mechanism by which there tend to be like habitable planets preferentially forming around low mass stars as opposed to higher mass stars.
Yeah, so that's I should say that's an active area of investigation. So we know statistically that's happening. The models exploring planet formation around low mass stars. So there's a couple of things to keep in mind. Again, the disks around these low mass stars tend to be lower mass. And in order to form like a Jovian planet, for example, you need to build up about 10 Earth masses worth of rock and ice before you can start creating the gas. So there's some threshold that, even if you're past the snow line around some of these disks, there may just not be enough mass to build a Jovian planet. So that might explain why the Jovian fraction of planets drops off pretty steeply with mass. The fact that we've got lots of terrestrial planets probably has a lot to do with the fact that these disks are more dynamically stable, right? They're orbiting a very low mass star, so the Kepler speeds are much lower. So things like collisional rates, the collisional speeds are much smaller. So you tend to get an environment where you're more sticky than collisional. And so that may allow more of these planets to form. The flip side of that is that if you make lots of little planets, then they'll start dynamically interacting. So again, since we're at very low numbers for these low mass planets, and we can't disentangle the planet formation history of stars that have no planets. Right? We don't know if they didn't form planets or they did form planets and they all dispersed away. There's still quite a lot of uncertainty about whether dynamical n-body processes are more important than the lower collisional environments in these disks. So there's a lot of questions around this, and so a lot of this is now being driven by modeling the process from the planet disk formation all the way to the point where you're getting the sort of interactions. I should say that the fact that the TRAPPIST planets are all in resonant structure means that they did interact early on. They could not have just formed in resonant structures. We have to migrate to that position. So that does, at least from a first kind of system, tell us that dynamics are important, but maybe not enough to disrupt the system. So this is an area of active research, and we're still trying to make the connections. But we know the ingredients for planet formation are there. We see disks, we see jets from very young low mass stars, and obviously now we're seeing planetary systems. Where the connection resides for the vast population of these is still unknown. Do you have a question?
Yeah, I do.
Yeah.
It's about magnetic fields. So one of the things we wonder about on Earth is when the magnetic field was first established.
Yeah.
And so you were talking about the demographic population you have of exoplanets and how you could look at them essentially being formed all the way through the system. And I'm wondering if this provides, supposing that one could map whether exoplanets have magnetic fields or not, whether this provide a mechanism for looking at how they get established.
Yeah, so the challenge is, again, one of the reasons we have all these different methods for finding planets is that we're always fighting with the overwhelming signal of the star. Right? And so that is definitely also the case when we talk about magnetic properties. And in particular, when we talk about low mass stars, as I mentioned, most of those stars are very magnetically active, have strong magnetic fields. So to tease out the whatever observable you want to make for the planet is really difficult. Now, there's one exception, and I did mention when I showed that plot, is that magnetic activity drops off with the lowest mass, stars and getting into brown dwarf region. So in those cases where you don't see a lot of activity from the host star, and yet we still see activity from the system, we think that that activity might be tied to the planet itself, and particularly star-planet interaction. And what I mean by that is really, kind of an analogy of the Io Jupiter system. Right? We think we're actually seeing aurora generated on the star from the interaction between the planetary magnetic field and maybe some evaporation off the planet and the stellar magnetic structure. So we have lots of models for these, and they produce some of the radio emissions we see from the very lowest mass stars. And the fraction of ground dwarfs that have radio emission is something like 10%, which is actually not, order of magnitude is probably a good estimate for how many of those systems have, planets that might be interacting. But at this point, we don't have a direct observable where we can say that this emission is definitely from the planet as opposed to, or a planet-star interaction, as opposed to just regular stellar emission. So that's the big uncertainty, is that we don't have good ways of measuring the magnetic fields of the planets. But at least in terms of, I mentioned the densities of the TRAPPIST planets, they follow the Venus-Earth curve. So they are likely to be, iron core, differentiated planets, so they have the possibility of generating magnetic fields. But how we go about confirming that is still a open question.
More questions?
Okay.
Then I don't know. So postdocs and students will still have space for lunch with Adam if you want to join his cover class.
Yeah, thank you. Coming. Let me go ahead and stop the screen.